Hello everyone, I'm Yixue from HKUST, and here I'm glad to present our work. Survival prediction is actually an ordinal regression task that predicts the ranking risk so that the population of high risk and low risk can be separated. It generally integrates the qualitative pathology data and quantitative genomics data. However, it still suffers from some issues. The first thing is the large size of pathology images. Another thing is there may be global structural consistencies between structural interaction of tumor microenvironment in pathology and co-expression pattern of genomics, which is ignored by the previous words. However, this may have significant associations with survival analysis. So, genomic data has been applied to guide the selection of patches by co-attention mechanism. However, they only densely calculate local pairwise similarity scores for selection. However, a local view may not fully learn information about TME, since the patches contributing to TME may spatially disperse throughout the entire WSI, which indicates long-range structural interactions. Similarly, it also ignores co-expression pattern between genes. These two potential structures might have the intrinsic consistencies, which can be utilized to select instances that are more associated with TME and further survival. In the context of how to leverage the global consistencies between the potential structures, we propose to mathematically formulate this problem as an optimal transport problem. In our work, we use OT to match patches and genes imbalance for stacking informative patches to represent the gigapixel WSI. As a result, instances that have high global structural consistency can be identified by OT. Here, we formulate patches of a WSI as a single batch of instances. The same goes for genes. With these two batches of instances, we use discrete formulation of OT to perform a structural matching, which is able to generate an optimal matching solution pi with the overall minimum matching cost based on the cost metric between pairwise instances under the constraints of total max equality. Here, we rewrite it with a metric form. Intuitively, the optimal P describes how to distribute instances of a pathology bag to a genomic bag under a trade-off instances within modalities for transporting, instead of only considering the local pairwise similarity, which means the global awareness. In a word, OT provides an instances matching process with global awareness. Once acquiring the optimal P, we can identify informative instances to represent the WSI in this way. Despite these advances in OT, due to high dimension of pathology backside, the original OT might suffer from high computational complexity. To address this, we propose a robust and efficient implementation. We train a model over microbatch for pathology. Further, we use a variant of OT formulation that is robust to subset sampling to approximate the true OT over microbatch. In this way, we succeed in reducing the computational complexity. We compare our work with SOTAS, and our approach achieves the high performance in 4 of 5 cancer data. In the Kaplan-Meier statistical analysis, our work also performs better in separating the population of high risk and low risk. We further perform the ablation study to validate the effectiveness of each component and investigate the robustness of the variant of OT over microbatch. On the left side, our method better balances the stability and precision over different sizes of microbatch. On the right side, compared with the original OT, our work always presents similar attention for different sizes of microbatch, which suggests the robustness to the subset sampling. Thanks for listening.